Today at our usual Wednesday seminar, we will listen to our local postdoc, Ali Fatemiabhari, who will tell us about the holographic vacuum misalignment.
Okay, thank you very much for giving me the opportunity. Today I'm going to talk about holographic vacuum misalignment. It's based on a work published in collaboration with Daniel Elander and Maurizio Piai in Swansea University in UK. And it's about a holographic approach to a composite Higgs model. So first of all, I will go through some introduction and background material about what the so-called hierarchy problem or the naturalness problem of the standard model is, and what are the proposed methods to tackle this issue. And then I will go through some gravity model, which will be holographically evolved to a desired four-dimensional theory, which will approach to tackle this problem. And then I will study the spectrum of fluctuations of this gravity model, which will correspond to the mesonic mass spectra of the field theory, and some results and the summary will flow, basically. So let me give a brief review of what the composite Higgs model is, and then I will go into more details as we go forward. So a standard model suffers from a problem called naturalness. The mass of the Higgs is much smaller than the cutoff which the standard model is believed to hold. And this causes some issues. For example, if we find a UV completion for the standard model, the mass of the Higgs may always remain as a free parameter. It might not be determinable from the UV completed theory. And basically, one of the few solutions for this problem is that Higgs not being a fundamental particle, but a composite state coming from a new sector added to the standard model. And this sector supposedly respects some symmetries at higher energies, and at lower energies, lower than the Tevez scale, this symmetry breaks spontaneously and produces some non-Bogoldstone bosons. And those will be identified as the standard model Higgs. Due to interactions with the elementary standard model fields themselves, there might be a small explicit symmetry breaking, and that will generate a potential for Higgs and a mass for Higgs. But the mass will be protected along the RG flow. So this is the broad picture of what a composite Higgs model wants to achieve. So now let me go into some specific details that how this hierarchy problem might appear in the presence of scalars in the field theory. So as a very simple time model, assume that in four
Excuse me,
dimensions we
Ali.
have some.
Are you showing
Sure.
another slide? Because I'm seeing all this time. I'm seeing the slide with the title,
Really?
the first slide. Maybe it's locally the problem of my computer. Sergey will tell us, but I'm seeing only the first slide.
Okay, yeah, also, I agree with Dmitry. I also saw only the first slide. And well,
I see. Okay, let me try again.
but now when you've tried changing, I saw you
All right.
change into the second slide.
Yeah. Without the
Okay.
full screen mode, you see all slides.
Okay, so I assume the full screen mode is not working properly.
No, it's not. The full screen
Okay.
mode is not working properly.
Okay. Okay, I will go from this. Okay, now you can see.
Yes, it works.
Thank
Yes.
you.
Okay. Yeah, so here I was giving a broad review that the composite Higgs comes from a new sector added to the standard model. And this sector respects some symmetries, and then they break spontaneously and also explicitly to produce the mass and potential for the Higgs. So to go into a more concrete example, assume a four-dimensional field theory with one scalar and one fermion, and there is a U-couple coupling between the scalar and fermion. So one naturally wants to see what is the corrections to the propagator of this scalar field, or what are the corrections to the mass coming from the quantum corrections as a result of interaction with other fields. So the first correction comes from this loop, including the fermion. And this is a straightforward calculation. One can calculate what is the effect of this fermion loop on the propagator of the scalar field. And depending on which scheme you choose, you reach to more or less this result, that there is a cutoff dependence on the loop integral value. And there is a quadratic divergence coming from the cutoff. There is a logarithmic divergence. And this logarithmic divergence is also proportional to the mass of the fermion and some finite contributions. So for a renormalizable field theory, this result is totally fine. One can introduce the counter terms for mass and for the couplings, etc., and absorb the infinities. And then one gets a proper mass for the scalar. The issue becomes a bit apparent when this cutoff finds a physical significance. So, for example, if we find the UV completion for the standard model, whether it is a string theory or whatever, then this cutoff will find a physical meaning. It can be an inverse of a string length or something like that. Then some peculiarities happen in our theory. For example, the Bayer mass will be the whole mass of the particle plus the corrections. And then if we think of this scalar as Higgs of a standard model with a 125 J mass, and the cutoff close to Planck scale, then the Bayer mass in the Lagrangian takes a very intriguing form. So this result means that a very slight change in the Bayer mass at very high UV completed theory will result in a drastically different Higgs mass. And this is called the fine-tuning problem or naturalness issue. So if someone wants to measure the parameters at the UV completed theory and go back along the RG flow and derive the mass of the Higgs at IR, it is almost impossible. Not only experimentally, you need to measure this Bayer mass up to 30 digits, which is very hard. But also theoretically, you need to include many, many orders of loops and non-perturbative correction.
So you probably meant 10 minus 34 is the first term and 1 is the second, compared to the upper line.
Yes, and so the this sigma 2 is lambda 2, and MP is 10 to minus 34
Yes.
lambda.
Yes.
Yes. Yeah. And so this result is only dangerous if the cutoff of the standard model is very high, meaning that the standard model holds up to near Planck scale. But there are good reasons that the standard model might hold up to data scales. It can predict well-observed proton decay if the cutoff is very high. If the cutoff is low, the theory needs to be changed a lot. So one might be concerned by this fine-tuning issue. Another issue is that the mass of the fermion appears here. So if there are very heavy fermions, they will also affect the mass of the Higgs, and they will never decouple no matter how heavy the fermions. So this was the provider for a scalar. For the fermion, none of these basically happen. when we calculate the corrections to the fermion mass, we get a result logarithmically divergent, and then there is one term which is proportional to mass of the fermion itself, but no constant quadratic divergence, neither term proportional to other terms in the Lagrangian. So there is a subtle reason for this. Basically, this Lagrangian, if we set m to 0, the capital M to 0, and the Lagrangian enjoys a chiral symmetry, which rotates the different chiralities of the fermion in different directions. And this chiral symmetry protects the fermion from getting any perturbative corrections in the mass. Now, even if we add the mass by hand, which we have done here, all of the corrections must be proportional to mass itself, not any constant term or any other parameter in the theory. So this is the so-called custodial symmetry, which this chiral symmetry is not there, but it acts in such a way that protects the fermion from getting large corrections to its mass. So there is this terminology by 't Hooft that the mass of the fermion is technically natural. We want to achieve such a thing for the Higgs itself. We want to write a theory which has a custodial symmetry and that is protecting the Higgs from getting mass corrections which are constant or depending on other parameters in the theory. So even if there is explicit symmetry breaking, it should be natural. So having said all of this, and this is how schematically a composite Higgs model will work. We assume that there is elementary sector, including the W and Z bosons and the gluons and most of the fermions. But Higgs comes from a new sector. And the sector is strongly coupled. At higher energies, it respects a symmetry group G. At lower energies, possibly at Tevez scale, it works spontaneously to some subgroup H. And there is a coset G over H. The non-movable stone bosons of the symmetry breaking are living there, and they will be identified as Higgs. And this subgroup H should be large enough to accommodate this U2 cross U1 of the standard model.
So just for completeness, what you said about fermions and bosons, one resolution of this problem is actually supersymmetry, right?
Yes. Yeah, exactly.
Yeah,
that's another approach. This one is without symmetry. The composite Higgs model is without. Yeah. So here, what happens beside the spontaneous symmetry breaking is that the elementary sector with SU2 cross U1 living inside, it will engage a subgroup of G. That will introduce explicit symmetry breaking from interaction with the composite sector, and that will produce a potential for the Higgs particle and a mass. And this process is called the vacuum misalignment. So if initially F is representing the wave of the subscalar in the composite sector, and the wave is respecting the subgroup H in the group space, and then due to explicit interactions with the standard model, the vacuum misaligns a bit, and this value of misalignment angle will enter into the potential for the Higgs, and it will produce a mass, the desired mass, etc., but the mass will be low. And since this composite sector is QCD-like, it is strongly coupled, studying it is not very straightforward. So one way which people usually take is doing some calculations by lattice field theory methods. Here we do it with holographic method. So in our case, and as I will go into details later, the G group will be SO5, and there will be a spontaneous breaking to an SO4, and this is the minimal composite Higgs model. because SO5 to SO4 produces 4 non-Boole-Son bosons, which is the minimum number of degrees of freedom required for the Higgs complex doublet.
Sorry, Ali.
And this,
Could you please repeat again? How do you see vacuum misalignment in this picture? So you have some group manifold G, that's the gauge group.
right. No, this is a global symmetry, G.
Oh yes. Oh, I see. It's global symmetry.
Yes.
Then it breaks down to very
H.
small group H, which preserves vacuum. Okay.
Yes. And then there is some explicit symmetry weakening coming from the standard model interactions, basically. So standard model interaction doesn't gauge the whole G. It only gauges a subgroup, SU2 cross U1. And if you gauge a subgroup of a global symmetry, the global symmetry will be broken, basically, because you are quotienting the field theory, basically.
I see.
And that will that causes the misalignment.
Misalignment in what sense?
In the sense that the vacuum will not respect H anymore.
I see. Yes.
Yeah.
Excuse me, can I ask?
Sure.
Is Ali here?
Yeah, I cannot hear you very well.
What is theta?
I think Dmitry asked the question what theta was in the picture.
Oh, okay. So this theta is the amount of basically misalignment. So initially this F, the direction of this F is not important, is not observable, and since you can pick H to be any surface perpendicular to F. But when there is an interaction which doesn't respect H, and then the expectation value of some scalar can take values which doesn't respect the subgroup H, and that theta is the amount which that symmetry is not respected anymore, basically.
So theta is a direction to the true vacuum, which is unique. Right?
Yes. Theta determines the true vacuum of the theta.
Thank you.
Yes. Okay. Yeah. So this was the field theory description. We want to write a gravity model which captures at least as much properties as possible we can. So we want a 4-dimensional field theory. So this 4-dimensional field theory normally should be represented by a 5-dimensional gravity here. But we want this 4-dimensional field theory to be confining and to produce a mass gap, basically. So one of the easiest way to achieve this is starting from a gravity from 1 dimension higher, a 6-dimensional gravity, and compactify it on a circle, and choose the specific solution which this circle shrinks smoothly to 0 size, depending on the radial coordinate of the ADS space. This is a prescription given by Wheaton at the first days of ADS CFT, and it produces a gravity dual to a field theory, which has a mass gap, and it shows confining behavior when one calculates the expectation value of Wilson loops. And this is what we will do. In the field theory side, there is a global SO5 symmetry spontaneously broken to SO4. So global symmetries in the gravity side will be promoted to local isometries. So we'll have a local SO5 isometry broken to local SO4. And finally, we want to introduce the elementary standard model fields. Now, so since this elementary standard model fields are weakly coupled, we cannot include them inside the bulk gravity. The bulk gravity is supposedly describing the strongly coupled regime of the field theory. So these standard model elementary fields will only be introduced as boundary degrees of freedom on the gravity side. So one thing which we do here is that in the field theory side, we want to weakly gauge SO4 by introducing the W and Z boson. Here we gauge SO4 instead of SU2 cross U1 because of technical difficulties. The boundary terms in the gravity are very complicated, and in this work or in this paper, we wanted to just drive the formalism. So instead of SU2 cross U1, we are gauging SU2 cross SU2 basically. And this SO4 is not aligned with the previous SO4. It is misaligned to produce to have the potential for the Higgs, etc. So this is explicitly breaking the SO5 symmetry, and from interactions of these two SO4s, and SO3 will remain, and that will act as a photon of our theory. So instead of SU2 cross U1 breaking to U1, it will be an SO4 breaking to SO3 or to some SU2. So the subtlety of the work here is the following. By weakly gauging some subgroup in the field theory, we are explicitly breaking the symmetry, and we want to introduce these terms at the boundary of the gravity. So it means that we are introducing explicit symmetry breaking terms at the boundary. And that will break the SO5 isometry of the gravity, and that is not going to end well. And we want to keep the gauged symmetry at the gravity always. So the way out is introducing some spectator fields of the spurions. These spectator fields at the boundary will transform in such a way that all of the explicit symmetry breaking will turn into spontaneous symmetry breaking. And only at the end of the calculation, we will freeze the spurion. We will take some limits in the parameter space. And the dual field theory results will show an explicit breaking result, although at the gravity level, everything is only spontaneously broken. And I will give more detailed descriptions when I show the symmetry breaking terms.
Excuse me. You considered in the four-dimensional model, you consider spontaneous breaking of a global symmetry, right?
Right.
So why do you consider explicit breaking of gauge symmetry in the five-dimensional model? So probably naively that should be spontaneous as well, no?
Yeah, so this SO4, which we are going to weakly gauge, is not the spontaneously broken SO4. This is a misaligned version. So it is another subgroup.
I mean the previous line where the global SO5 is broken. No, the previous line in this table where the global SO5 is broken spontaneously to global SO4, right?
Right.
But in five dimensions, you explicitly break SO5, local SO5, to local SO4. Why explicit? Why not spontaneously?
No, this part is spontaneous. This part is definitely spontaneous.
Okay. So you had explicit breaking by gauging the subgroup, right?
Yeah. We want to add, we want to gauge subgroup, but at the gravity level, doing this is a bit complicated. We are adding some boundary terms which breaks the symmetry explicitly, and we don't want to do that. So we add some spurions to compensate for the problem, basically. Then at the end of calculation, we take a limit which we get rid of a spurion.
Okay, thank you.
Yeah. Okay. So here I will start giving description of the field content of the gravity side. So as I mentioned, the gravity should be a 60 theory plus some boundary terms. So the 60 theory is a minimally gauged gravity. It's a bottom-up model. There is a Ricci scalar, and there is a scalar called chi with some potential. and the scalar is charged under gauged SO5 symmetry with this FMN type of Lagrangian. The potential is chosen in such a way that it respects the SO5, and it only depends on the modulus of the scalar field here. And there is a free parameter delta in the potential, which because our model is bottom up, it doesn't come from first principle supergravity. It is freely chosen, and one can have background solutions which gives a non-trivial profile to the scalar phi. Hence, the SO5 symmetry can be spontaneously broken to SO4. And then we describe this scalar chi in terms of a nonlinear sigma model with modulus phi and the coset directions parameterized by pi fields. And this SO5 over SO4 coset pi fields will be basically the Higgs complex doublet for us. So the symmetry breaking pattern will be for the gauge field 10 to 6 plus 4 initially, to SO4 degrees of freedom, and the scalar 5 will be broken to 4 plus 1. Later, when we add the boundary terms, this 4 degrees of freedom will be broken to 3 plus 1, and that one extra field will be the massive Higgs scalar, and the other 3 will be eaten by the gauged degrees of freedom to produce the massive W and Z boson. So before adding the boundary terms, so in the UV we have in CFT dimension 5 defined by the insertion of an operator dual to the field phi with some scaling dimension given by delta. And when we study the solution of the gravity at the UV, 2 parameters will appear, 2 free parameters. One of them determines the coupling of the dual operator, and one condensate associated with the dual operator. And this is the normal ADS CFT dictionary, basically. And now we want to go to one lower dimension by doing a normal Kaluza-Klein reduction along the 6th direction. We call it here eta. So from this Kaluza-Klein reduction, the metric will produce a 5-dimensional metric plus 1 scalar chi and 1 vector chi m. And the metric and the scalar part of the Lagrangian will look like the following. Again, we have the previous potential with insertion of this chi field. And the background solution which we want to study sets all of the fields to 0 except the metric itself, the phi field and the chi field. And also we assume that the 5-dimensional metric takes a domain wall form, as can be seen here with this dx213 representing the field theory directions, and rho the radial direction of the so-called energy direction. So if we want to look at the UV expansions more explicitly, at the large rho, the phi goes to critical value of the potential, and chi and a are chosen to satisfy the equations. So in terms of z coordinate, which is the coordinate change from rho to z, we have this famous expansions for the field phi with 2 integration constants. One phi j is the source for the dual operator, and phi b is the associated condensate. And the explicit form of this expansion depends on delta case by case, and each case needs to be done separately. For example, for delta equals 3, the expansion looks like the following, with all of the terms given in terms of phi j and phi b, etc. So for the same asymptotics, there can be different solutions in the ball. And we are interested in specific subclass of them. So the one which we are specifically interested in is some solution which the circle parameterized by eta shrinks smoothly to zero size at some finite radial coordinate, value of the radial coordinate, for example, rho 0. So this will produce the famous cigar-like geometry. And in order to circle shrink smoothly, one needs to be careful to choose parameters very nicely. And instead of 2 degrees of freedom in the IR expansion of the fields, we have 1 degree of freedom, phi I. So at the end of the day, one can extrapolate to UV, and this phi j and phi v will be given by phi I. So one thing which happens here, and we have studied these in previous papers by my collaborators, is that for large values, so for some values of phi I, the background stops becoming unstable and producing tachyonic instability. And in those regions, there are other solutions with other asymptotics which can take over. They have their own problems. But the thing which is important for us here is that we will work only in the range of parameters which the confining solution is reliable and its free energy is favored respective to the other solutions. And this will be our main background. So building on this background, we also want to add the boundary terms. So these boundary terms are important for many reasons. The most important one is that during the renormalization process or the holographic renormalization process, we need to have boundary term for each of the fields in the ball to absorb the infinities coming from the IR divergences in the gravity corresponding to the UV divergences in the field theory. So, for example, there are the famous Gibbon Haugen terms and another term we call S lambda to absorb the infinities to have a well-defined variational problem for the gravity and also absorb the infinities. And then we have some specifically chosen terms for our other fields. For example, we introduce kinetic terms for the gauge field at the boundary. And here we want to introduce potential for the Higgs coming from interaction with other fields. And this potential will basically break the symmetry explicitly. And that is where we introduce a new dynamical field called P5. And it is changing, it's transforming under SO5 in such a way that to compensate for the any symmetry breaking effect coming from the chi field or from the potential. And the Lagrangian for the P5 is written above. It has a kinetic term and it has a potential. So it is rendering the explicit symmetry breaking in the misaligned direction to a spontaneous symmetry breaking at the gravity level. Towards the very end of the calculation, when we derive the equations of motion, we will freeze the sporium. We will take limits, which makes the P5 non-dynamical. It takes a wave in the misaligned direction, and it will induce the explicit breaking as we desire. So all of these coefficients appearing in the boundary can have an infinite contribution to absorb the infinities during the renormalization. They also can have a finite value. And those finite values are crucial for us. So for example, when you want to gauge an SO for subgroup, we keep a finite contribution from D2 bar. And that will be, for example, the would-be gauge coupling of the standard model. And also we have a boundary term for the scalar field too. So to have a summary, we have a lot of terms introduced and a lot of parameters, but at the end of the calculation, very few of them will remain. There will remain parameter V, the misalignment related to the misalignment angle, M4, which will be the mass of the Higgs, and the parameter epsilon, which will be the gauge coupling of the SO4. And the KX also remains to address a subtlety related to our confining background. So I may describe it at the end if we have time. But its specific value is not important as long as it is not zero. So these three parameters will play a crucial role to fit with the data. So if there is any questions up to here, I can take it. Then I will go to the fluctuation. Okay, so this was a description of the background with Lagrangian and the boundary terms. Now we want to study the fluctuations around this background, and holographically this will give the mesonic spectrum of the field theory side, and that is what we want to achieve basically. So what happens here is that at the end of the day, we have a gravity coupled to some fields, and some of our scalars are taking non-trivial profiles in the bottom with their specific potentials. So the gravity has a lot of diffeomorphism, gauge invariance, and that gauge degrees of freedom needs to be fixed very carefully. And if you have also scalars inside the theory, the scalars will mix with the gravity. So gauge, we need to be careful at gauge fixing to not include any non-gauge invariant terms. So yeah.
Sorry, I got distracted. Could you stop for a second and review what is actually the model? Are you embedding into supergravity? Are there some brains involved, or
no? So okay,
what's the setup? Or you just consider gravity coupled to what? Gauge fields or scalars?
Yeah. So this is a bottom-up gravity.
Yes.
Originally in 6 dimensions with a SO5 gauge field and a scalar. It's just that.
Just that. And
yes.
So all you want to use is that there is an ADS kind of solution.
Yes.
And then that may give you some hint about strong coupling limit of boundary.
Yes, it will give a spectrum for a strongly coupled field theory, which its field content is not known to us, I can say.
And
but it's mass spectrum.
So what you want to learn is what? Mass spectrum of these fluctuations, or what?
Right. So what we want to achieve is that we want to have a light scalar, much lighter than the fluctuation. So if we want to have a large gap, as I will show later, and satisfying some bounds coming from basically the standard model that besides the scalar, there should be also a vector which is more or less at the same mass as the Higgs, playing the role of the W and Z model.
Okay, thank you.
Yeah.
And I also ask a question. You have a lot of constants in this model, like in breaking terms, etc.
Right.
How are you going to fix this constant? Is it some theoretical considerations or literally from experiment?
Right. So yeah, I will show you the final results, how they will look like, and how we will gradually fix the values. But some of the data from the background, for example, this phi I and the delta, they are more or less free to choose. The reason they are free is that because we are in a bottom-up model, and this is not a top-down, which there are less parameters to play with. But the important fact is that the results which we derive are not fine-tuned depending on these parameters. So there is a very wide range of parameters which we can choose, and we can derive the desired theory. But this is a toy model for a top-down, which is going to be done later. That is why there are like a lot of free parameters, basically.
Yeah, so basically,
but they will be chosen
you find these parameters from experiment, right?
Yeah, most of them, yes. Most.
Okay.
Yeah. Okay. So yes, we have gravity coupled to some specifically some scalars and also some other fields like vectors, but they don't take away. So we want to find gauge invariant combinations for the scalars and the metric. So there is a well-tested formalism for this, for scalars fluctuating around the background value, and for a metric which takes basically a dominant form, as our case, we can decompose the metric to radial part and transverse part, transverse fluctuations basically. And this transverse can also be later decomposed to the traceless part, the vector transverse part, and the trace of the metric, this small edge. And there is a specific combinations in this setup, which gives gauge invariant combinations which will survive the process of the deformorphism. For example, the important part for us is this A, called A fluctuations, which are mixing the fluctuations of the scalar with the trace of the metric. And all other combinations are chosen in such a way that they decouple from these degrees of freedom. They're either gauge non-invariant or they're algebraically given by the equations of motion. So there is no dynamics in it. So the dynamic part for the fluctuations of the scalars come from the scalar itself and mixing with the trace of the metric. Another part which survives is the transverse traceless part. I will give the equations later. So for the scalars, we have the following equations from the fluctuations of the background, with a relatively simply given terms. For example, this chi field are given in terms of the potential of the background scalar, etc. And from the boundary terms which we have added, also the scalars will develop a boundary condition over the fluctuations. And basically our job will be solving these equations to find a discrete mass spectra if there is a mass gap. This is for the scalars. For the transverse part of the transverse traceless part of the metric, we have other equation, and for the transverse polarizations of the vector coming from the metric, we have another equation. And there are similar equations for all other degrees of freedom too. And our task will be solving these on the specified background with the determined boundary conditions numerically. And this will be how the results start to look. So here I am showing just the fluctuations of the scalar corresponding to the would-be Higgs field. And there are three of them. Here we cannot show all the three, but there are three of them. And there is one scalar in the cross purple form. When we dial the mass M4, we can give some mass to the field, and there is a gap between the first state and the higher excited states. And this is gradually what we want to achieve. So now I can show you the whole spectrum, how it looks like. So in each plot, we fix all of the parameters except one. In the left panel, we are changing the misalignment angle. The plots at the bottom, they are zoomed versions of the plot at the top. So one can see here that we are able to choose some values for the coupling in such a way that the mass of the Higgs is fixed to some value, and the mass of this green state, which is the would-be W or Z boson, is increasing as the misalignment angle is increasing. And also there is a massless photon in the spectrum. And besides these three states, which are coming from here, there is a huge gap, and this gap is produced by choosing some very reasonable values for this M4, epsilon, and V. And there is no fine tuning up to very high digits, basically. And also similarly, the dependence of the mass of the gauged vector boson on the coupling is, as it is expected, it's like quadratically increased. And again, there is a mass gap here. So here, for example, the epsilon is chosen to be exactly what the coupling for the W boson will be in the standard model. Then this is a final result showing all of the parameters fixed in such a way that it produces a semi-realistic model. And again, this purple line is the Higgs, fixed, normalized to have mass 1. And the Z boson is 40% lighter, as the standard model will require. There is a light photon. Then the first scalar excitations appear at more or less 20 times heavier, which would be more or less 1 TeV. It is the limit which CERN puts on the observations. No state has been observed between Higgs and higher masses. And the first vector excitations appear at almost 32 times heavier than Higgs. And this is again a bound set by CERN for the heavy vectors in the spectrum of the standard model. And basically, these two requirements are matched by tuning the mass of the gauge coupling epsilon and the mass of the Higgs or misalignment angle. So we use these 2 or 3 parameters to produce a desired tune. And the achievement is that that we can do this without heavy fine tuning. Okay, so to give a summary, we had a bottom-up model with a smooth gravity background without pathologies, and describing making a confining theory. And we were able to calculate the mass spectrum of these states. And we did basically the main achievement of the work is that we inserted the field theory degrees of freedom inside the gravity without breaking any symmetries explicitly. And we treated both the strongly coupled regime of the field theory and the weakly coupled regime of the field theory inside the gravity without any pathologies. And the Higgs boson and the would-be ZW masses were more or less at the desired ratios. So the aim, the obvious aim would be, instead of gauging NSO4, gauging NSU2 cross U1, and also possibly including the fermions. The fermions are more complicated, whether they will go inside the bulk of the gravity or they will just be introduced in the boundary. And there have been vast studies for the inclusion of the fermions in the QCD standard model, and there are different perspectives on what should be done. And more importantly, doing this calculation in a top-down model. For example, there is a very nice 7D gauged SO5 gravity, and the Romans 7D gravity compactified doubly on the torus to obtain a 5D gravity with a gauged SO5. That is a candidate model for studying the same mechanism. And in the top-down model, there will be definitely less free parameters. And that should be an actual test whether one can produce the appropriate mass gap to fit with the required experimental bounds. Okay, thank you very much.
Thank you, Ali. So, questions?
I have a question. So it would be nice to have kind of more systematic embedding into some ADS CFT setup where you have controlled description, where you know how to compute corrections, for example, or something like that.
Sure. Yeah, so the main problem is that there should be a well-defined like SO5 supergravity that also admits a confining solution. Yeah.
Okay.
Right.
Yeah, but
sorry.
you kind of
Yeah. Yes, I forgot to ask. So you mentioned this misalignment, but there were also models Technicolor. Is that
Right.
uh,
Right. So the Technicolor is ruled out. The difference of Technicolor with our model relies on the fact that Technicolor is the theta equals pi over 2 limit of our calculation. Technicolor is more or less Higgsless, meaning that it doesn't have a light Higgs in the spectrum. All of the non-Bogoleston bosons get absorbed to the field theory and get absorbed to the gauge bosons, and that cannot satisfy the bounds of the experiment. So the Technicolor is ruled out. The composite Higgs is in between Technicolor and the standard model Higgs, which the standard model Higgs has only one scalar, but here we have a new sector, and we can keep it light, basically. The whole point is that this theta needs to be small to have a light Higgs.
I have the following question. Suppose you constructed your invented a consistent holographic model, right? For this composite Higgs, so that you
Right.
can calculate corrections, any number of corrections.
Right.
Do you need a four-dimensional theory which is dual to this five-dimensional theory? Can you say that five-dimensional theory is enough? This is my description. I get all experimental predictions and they're consistent, so I don't need this is kind of my description of four-dimensional theory, but I don't know the four-dimensional theory. Do you need the four-dimensional duality? Do you need the
Yeah,
duality?
okay. So what I can say is that as long as some specific observables related to Higgs are concerned, probably the holographic dual will suffice. But at some point, one day, people want to do probably more calculations or studying deeply the model. Then the field theory definitely should be known better, at least the field content. And that is why the top-down models are more valuable, like, than a bottom-up model. Yeah.
Excuse me, I didn't understand. My question is not about top-down or bottom-up, right?
Okay.
My question is about the five-dimensional model without duality. You don't have duality. You don't even aim to create a duality
Oh, you mean
in the two models.
sorry, I didn't hear the last part of the question.
Where will you run into inconsistency if you have only one part of the duality, namely the five-dimensional model or six-dimensional
Right.
in your case?
Okay. You mean I think I didn't understand the question.
My question is related to the fact that you use only five-dimensional model and not the
Right,
four-dimensional model, and you do not have an exact duality between the two models, right? You
right.
claim that you describe some four-dimensional model, but you don't know whether you even describe some four-dimensional model. Basically, you have a five-dimensional model for our universe, for our experiments. So, do you need the duality at all? These words
Yeah,
about
so
duality, where will you see the
okay, so
contradiction?
the part,
Non-locality
so
or some?
this field theory is supposed to be strongly coupled, and in the 4D, you cannot derive the mass spectrum of the system without using duality. That's what we are doing, I guess. Is that
No, so maybe we can discuss later.
Yeah, I guess if I understand right,
okay?
if I understand right, so what Ali was talking about is not really. Oh, could you switch off your microphone?
Ah,
Uh, yeah, so it's here the five-dimensional model is just purely artificial one. It's not our real world. It's just to describe strongly coupled gauge theory.
Yeah, it's a model just to describe a strongly coupled ratio. Yeah, exactly.
yeah, that's his approach. But my question was, what if we consider this seriously as a model for our four-dimensional world, actually, without any duality, without words about strongly coupled theory, just this model, maybe make it more consistent and related to some string theory, to make it it consistent quantum mechanically, right? To calculate corrections, etc. And maybe that's enough. Produce any kind of experimental data.
Right. Yeah, I think I understand now that you want to assume that we live in a 5D in such a theory, 5D theory, and possibly we live at the boundary, and everything is given by this five-dimensional theory, right?
Yeah, this is just an artificial theoretical construction to calculate experimental data, but there
Right.
are
Yeah.
no dual, no four-dimensional dual.
Right. Yeah, that I'm not sure in at what level you will find a contradiction, whether the fifth dimension will um, probably might be observable to people who are living in five dimension, but is not observable to us. But yeah, I'm not sure about.
Oh, okay.
Yeah,
Mm.
yeah, that I'm not sure.
Yeah.
Okay. If there are no questions and no any more questions, then we're going once, we're going twice. Okay, then Ali, thank you very much for your talk.
Thank you very much.
Yeah, appreciate if you could send your slides to us so that we put it on the seminar page.
Okay,
And
sure.
see you soon.
See you later. Bye.
See you later. Bye.